That was actually a watershed moment, just to see that we could actually image through the polar cap.
Hello, my name is Andrew Gary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. In this episode, I speak to Nathaniel Putzig and Fritz Foss, co-authors of January's The Leading Edge cover article, 3D Imaging of Mars Polar Ice Caps Using Orbital Radar Data. Nathaniel Putzig is a senior scientist at the Planetary Science Institute. He's worked for 14 years with terrestrial active source seismic data in academia and industry, and presently serves as the U.S. Deputy Team Leader for the Shallow Radar Sounder on the Mars Reconnaissance Orbiter. Fritz Foss has worked in various capacities in the oil and gas exploration business for the past 23 years. He co-founded Unified GeoSystems in 2009. Remote sensing on Mars, next.
Well, basically, remote sensing is detection and measurement of physical properties of an object without coming into physical contact with the object. In the case of the shallow radar or SHARAD instrument on board the Mars Reconnaissance Orbiter, or MRO, a radio wave signal is transmitted. It propagates through space and the Martian atmosphere, reflecting off the Martian surface and subsurface dielectric interfaces, which are interfaces similar to acoustic impedance interfaces in seismic, which the listeners are probably more familiar with. And the reflected signal propagates back through the Martian atmosphere and space to a receiving antenna on board the orbiter. And then it's converted to a voltage signal, and it's sampled, recorded, and transmitted back to Earth. This signal is processed and analyzed to ultimately infer physical makeup of the surface and subsurface from which it came, in this case, Mars. This really is the essence of applied geophysics, namely to use geophysical methods to probe a target with signals, recordings of which are processed and analyzed to infer physical properties of the targets. Seismic itself can be considered remote sensing, even though we're in contact with the surface of the Earth with seismic, or the very near surface. We're generally interested in deeper targets.
This shallow radar instrument that you've mentioned, the SHARAD, is something that you focus on in your article in The Leading Edge. You're basically exploring the equivalent of the North and South Pole on the Earth. What significant discoveries has this instrument found?
Oh, there's been quite a few. So prior to the creation of these 3D volumes, we have amassed many thousands of so-called 2D profiles along, individual orbit tracks as the orbiter goes around the planet. And the highest density of the coverage is in the polar regions, because the spacecraft is in a polar orbit. So every orbit, it crosses both poles. We don't necessarily acquire data on every orbit, but many of them, probably 30 to 40% of the orbits, we're acquiring data over the polar caps. And so with this, large volume of 2D tracks, we were able to understand a lot of the interior structure as well as compositions in the polar caps. So some of the more important findings early in the mission, after just a few of these passes, we quickly came to realize that we could in fact see through most of the layers all the way to the base. That was actually a watershed moment, just to see that we could actually image through the polar cap. And then we realized that meant that there was very little lithic dust and sand intermixed in the ice, and therefore it was fairly pure water ice. And so that gave us an understanding of how long it takes that signal to propagate into the subsurface and back out, which we could then use to determine how deep it is to that base. And to our amazement, we discovered that the base of the ice is extremely flat-lying. And if you know much about glaciology on Earth, you realize that glaciers on Earth tend to press down, the weight of the glacier presses down on the crust of the Earth, and a compensation of that in the mantle occurs such that the crust is depressed by many hundreds of meters under a large glacier. And then we were expecting the same phenomenon to occur on Mars, and yet to our ability to measure it, there really is no lithostatic compensation of the load. So this gave us a new understanding of the heat flow from Mars' interior and the nature of the mantle on Mars. So this was a completely unexpected result from Sherrod. We weren't really expecting to learn anything about the deep interior from this experiment, but it just sort of popped out of all of those things. And another profound discovery with Sherrod was in the south polar cap, we noticed these odd zones where we were getting very low signal returns, what we call reflection-free zones, because they're basically these are zones in the subsurface that have no reflections whatsoever. They look like the background noise that we get from the time above the surface. And we were able to constrain the geometries on one of these zones well enough that we could understand the speed of the wave traveling through that material, and again, understand what its composition was. And in this case, it wasn't consistent with water ice, it was consistent with CO2 ice. And now we know that the Martian atmosphere freezes out every winter. About a third of the atmosphere freezes out on either pole in the winter hemisphere. And then, most all of that sublimates back into the atmosphere in the springtime. But what we didn't realize was that there were these large deposits of frozen CO2 trapped just beneath the surface of the polar cap. In fact, when we measured up the quantity of CO2 ice, we discovered that there's enough CO2 buried in there that if you released it all into the atmosphere, it would double Mars's atmospheric pressure. And this is important because if you double the atmospheric pressure, then there are larger regions on the planet where water ice can be or liquid water can be stable at the surface. And so this may help to explain some of the the features that look like they're eroded by water in recent times, geologically speaking, that we couldn't quite understand how you could get liquid water with the current atmospheric pressure of Mars. But if you double that atmospheric pressure, then it becomes easier to explain these apparently water-carved features on the surface.
Hi, I'm Dean Clark, and if you're enjoying this episode on remote sensing, you should check out my book, Remote Sensing in Action, The Curious Case of Sherlock Holmes and Albert Einstein. Anders Robinson and I have used the enormously popular fictional characters created by Sir Arthur Conan Doyle to unravel and explain the historical underpinnings of remote sensing. Visit seg.org and search Sherlock Holmes to learn more.
In the press, one hears a lot about discoveries of hydrated minerals, and these are important because it gives you a history of where water has been interacting with the surface of Mars. And of course, we're all interested in water because it has such a profound impact on climatological processes and sustains life. So the interest in water is we come at that from two different directions. The interest in whether or not life could have ever existed on Mars is tied up with understanding the history of water. And then if humans do go to Mars, as NASA is now intending to do in the 2030s, we'll need water to sustain our own lives there at the surface of Mars.
The first part of your paper's name is 3D imaging of Mars. What contributions have been made possible by utilizing 3D imaging of Mars?
Prior to us, embarking on these projects to do 3D imaging with the Sherrod data, the scientific community was doing research using the along track observation profiles, the radar profiles that are collected with the Sherrod instrument. And so in order to do geologic mapping using the radar data, these profiles would all be either kind of interpreted independently and somehow mapped using interpretations on the profiles, brought into an interpretation system similar to those used, or in this case exactly used for seismic interpretation. One of our partners in all of this is Sizeware Inc., and they make a software, interpretation software, that they graciously provide to THAN in particular to do interpretation with these radargrams. Well, several years ago, THAN brought me into his office and asked me, having a background in oil and gas exploration, and familiar with interpreting seismic, he asked me, would there be any real showstoppers in treating charade data in 3D? And, I couldn't think of any at the time. So we embarked on all this to first do three-dimensional radar imaging with charade data over the North Pole. And then we embarked on doing the South Pole. And we've managed to treat in 3D all of the charade radar, a large subset of charade radargrams, which are the radar profiles in 3D. And the treatment of the 3D, the charade data in 3D revealed some, interesting difficulties, I could say, in doing that. One of which was the time registrations of all the individual radargram profiles. It turns out that one of the things that we don't have to worry about in seismic exploration is the ionosphere. And the ionosphere is kind of a dynamic soup of electrons and particles that interfere with the propagation of, or influence the propagation of, radio waves. And in so doing, it causes the radar to return to the, propagate through and then return the reflections to return back to the spacecraft or the instrument at different times, or with some phase distortion. And accounting for all of that phase distortion between all of those independently acquired radargrams turned out to be kind of a big issue for us. And we managed to do it pretty well in the end after several iterations of trying to figure out what was going on there. And in so doing, we've improved our ability to handle the ionospheric distortion. And in fact, we have some additional cards up our sleeve to do even better on that. So the volumes, the 3D volumes that we've produced thus far are kind of the baseline 3D volumes. And we are kind of our next step here that we're embarking on right now is to go in and refine the treatment of all these individual radargrams in terms of their ionospheric phase distortion or even instrument phase distortion, and get the radargrams even better registered in time so that the 3D volumes that we produce are as high resolution as we can possibly make them.
So I'd add to that, in that one of the key things here for getting a better view of the subsurface has been the correction that the 3D imaging provides to the geometries. So for instance, on a single orbit 2D profile from one of these charade passes, you get reflections not just from the track nadir point, directly below the spacecraft, but also from other features, typically topographic features, off to the side and in front and behind of the spacecraft. And so these appear in the 2D profiles as interfering signals. So they're in radar parlance, they're typically referred to as clutter. And there are ways that we go about trying to model that clutter so we can understand that in fact that is clutter, and then you just sort of dismiss it as noise and try to interpret through it. Whereas with the 3D processing, that clutter suddenly is transformed into a signal, and it is put back where it belongs geometrically, and that then enhances that particular point in the 3D volume while potentially removing that clutter from other features in the subsurface that you were trying to image. And so this has worked quite tremendously well for both of these volumes. And it's really helping us dial in much cleaner view of what the subsurface structures are.
Let me add on to that most of the travel time that the radar propagates is in space or the Martian atmosphere, and a very, very like 2% of the time is spent actually propagating within the ice caps. And it was quite a large logistical problem to handle all the extra non-signal up above the ice caps, and we managed to do that through a process that seismologists, geophysicists are familiar with, called downward continuation. And downward continuation basically algorithmically takes the recording platform down closer to the surface. So it's as if you record the radar much closer to the surface than you could ever fly. And in so doing, we strip away all of that stuff that's not signal, and things become more focused just through that process. And then we follow that up with what we're familiar with in seismic called migration, 3D migration, and that positions things in space, time to their reflection positions, and that refines the focusing and the image that much further. And as Than said, those processes have turned clutter into signal, and we've been able to image the interior of the ice caps far better than we had ever done before.
As you mentioned, this article is in the January edition of The Leading Edge. It is the cover story. What do you hope readers of your article and your work take away?
From my perspective, I hope that they read the article and certainly learn more about Mars, through the work that we've done and continue to do with the Sherrod data. I would hope it inspires people to become more interested in planetary science, not just for Mars, but other planets or space in general. But also the tools that we've used. We've kind of bridged the use of tools that have been around and used routinely for terrestrial exploration for resources, kind of taken those tools and applied them pretty directly into to solving some problems and analyzing data in the realm of planetary science. And having that inspiration to meld the technology into two different application areas, I think is something that I'd like readers of the article to think about.
I guess I would add that I'd like people to maybe get a closer understanding of how planetary science can benefit our understanding of the Earth as well. As we all know, the Earth is a very complicated system. There's a lot going on here with the continents and oceans and the changes in the atmosphere, some of which we may have been involved in, and certainly life in general has contributed to the oxygen content of Earth's atmosphere. That's pretty clear. One of the beautiful things about planetary science is you get these cases like Mars where things are somewhat similar to the Earth. There's a day just a little over 24 hours. The tilt of the spin axis is very similar to the Earth. So it has seasons like we do on the Earth. And yet there are no oceans. There's no macroscopic life. There may be microbes in the subsurface. The atmosphere is almost 95% of CO2. And so in many ways, it's a simpler system. And so we can hope to understand all of the things that are driving it. This is an example of, using the technologies that we've developed on the Earth to go to other places and get an understanding of how these processes work. And then we can bring those back to Earth and perhaps shed new light on understanding similar and analogous processes here on Earth, such as the climate changes that are going on around us.
It's encouraging speaking with you both. It's nice seeing you both smile at various intervals, and the excitement in what you're talking about is pretty clear. Looking at what you all are doing, what are you most excited about when you look out over the next 5 years?
I would say one of the things I'm really looking forward to is, as Fritz was discussing, immediately we're working on getting a better resolution 3D products for these polar views. But at the same time, we're also looking at other features on the planet that could potentially be more accessible to manned missions. The manned missions are unlikely to go to the polar caps because, as with the Earth, they have very long polar nights for months and months when the sun doesn't come up. And that makes it very difficult to sustain a mission. So they aim towards the closer to the equator and the mid-latitudes. But as I mentioned earlier, they're very interested in water, be it in ice or liquid form, to help sustain the mission, both for generating oxygen to breathe and fuel for the activities on the ground, and fuel for the rocket to return to Earth, assuming they're coming back. In addition to the discoveries we made with Sherrod on the polar cap, we've also found a number of ice-related features in the mid-latitudes, in particular what are known as debris-covered glaciers that form around mesas and valleys. And they're basically glaciers that have been preserved under a layer of rocks and dirt and dust. And so we're hoping to use the 3D work to better characterize these glaciers. They are in these valleys and along the mesas, and they're fraught with this clutter problem as well because of all the topographic relief. And we're requiring enough density of coverage on a number of these glaciers that we should be able to apply the same 3D technique. And in tandem with this, we're also borrowing some techniques that were well developed by the seismic industry, a different technique that essentially improves the vertical resolution of the data a bit beyond what you can do with just standard sort of processing. So our colleagues in Italy are kind of leading the way on applying these methods. And they're showing very promising results such that we may be able to improve our vertical resolution to the point where we can see the top of these ice layers like those glaciers. Currently, we don't image the top of the ice, we image the bottom of the ice in the glaciers. So we're not quite sure exactly how deep it is. If we can improve our vertical resolution by a factor of 2 or so, we may be able to spot the tops of this ice, and that would be really useful information if you're going to send a mission to go mine the ice. One thing that I mentioned earlier was the CO2 ices that we discovered with Sherrod, and how the ones that we identified are sufficient to double the atmospheric pressure. Well, that may sound like a lot considering Earth, but the atmospheric pressure on Mars is quite low. It's 6/1000ths of the Earth's atmospheric pressure, so it's very tenuous. So doubling that goes a way towards where you might want to be if you want to have liquid water stable, but you really have to do more than just double it to make a really significant change in the climate. We do see more of these so-called reflection-free zones in other areas of the South Polar Cap. And to date, we have not been able to constrain their geometry and figure out whether they're CO2 ice as well, or if there may be just some other super clean water ice that's not producing any reflections. And there are some reasons to believe that the latter may actually be the case. But we're hoping with this new 3D, or perhaps with the enhanced 3D that may come later, we'll be able to figure out what the composition of these other reflection-free zones are, and that could potentially increase the potential for atmospheric pressure by many-fold over what it is currently.
To add from kind of the processing side of that, one of the forthcoming investigations that we're going to do with the 3D data is to try to iteratively refine the velocity model that we have for the ice caps so that we can have a model that's representative of actually what the propagation speeds are within the ice to as fine a level as we can get in order to infer what the actual materials are there. And so it's quite clear when you examine the radar returns as processed in 3D or even in 2D that the ice velocity and thickness of the ice really impacts the signal, the shape of the signal in time. And so if we can exploit that variation in the shape and time by doing a velocity analysis through an image refinement, then we hopefully will discover or have direct measurement of the velocity information within the ice, which will then tell us a lot about the physical properties of what the material is.
One thing that might be worth pointing out, in the seismic world, one can often get at the velocity of materials in the subsurface by looking how the timing varies with offset between the sources and the receivers. We don't have that capability here because our source and receiver is the radar antenna.
Right.
And so they're essentially zero offset.
So there's no move out.
There's no move out to speak of. So,
but there is move out in the image.
Yeah, so we need to resort to the imaging to figure out what the velocities are.
At seg.org/podcast, you will find the show notes and links to the article and animated videos of the Mars Reconnaissance Orbiter. If you enjoy the show, review us on iTunes. Your review helps others find the show. Season 1 of Seismic Sound Off is sponsored by the SEG Wiki, home to hundreds of biographies of key geoscientists, geophysical tutorials, and core content from the science of applied geophysics. Visit wiki.seg.org to learn how you can grow the world's first online geophysics encyclopedia. Original music by Zach Bridges. This episode was produced by Isaac Farley and hosted, edited, and produced by me, Andrew Gary. Special thanks to Steve Brown, TLE Managing Editor. Thank you for listening. This is Seismic Sound Off, signaling off.